All right, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I started doing these when the pandemic set in, and my original concept was that there were all sorts of kids who were not in school at that time, and this was kind of a way of providing some hopefully interesting content to fill in for that. That story is rather over at this point. But I've continued doing this because I find it interesting. People seem to like it. I learn lots from it. But I would like to get input from people on what kinds of things they would like to hear about or see here. I think I'm going to, there are questions where I've already answered them, and I think we're going to mostly point people to the existing answers when that happens. I also might talk a little bit more about things that I think I'm probably uniquely able to talk about, although I always find it interesting to try and explain things that in principle you could find explained elsewhere, but somehow I end up having different explanations than you would often find. Kind of reminds me of a little bit my old friend, a physicist named Richard Feynman, who was quite famous, who wrote a collection of lectures on physics based on, well, in the early 1960s. And I remember him telling me that when he had first had, he presented physics in kind of very much his own way, which was an interesting and very intuitive way. But when he was first giving those lectures, he had some students taking notes from them. And he told me that they'd come to him and said, well, you know, in your lectures, you explained this thing in this way, but Professor Feynman, we think that the standard way of doing it is what you wanted, and so we changed it to be the standard way of explaining this thing. And he was like, oh my gosh, no, don't do that. The whole point is to explain it in a way that hasn't been explained before. So after that, he got some fairly distinguished professors actually to take the notes for his lectures, and that's what turned into a fairly famous collection of physics textbooks. But so even when one's asking about something that is kind of a thing you could find the answer, an answer in a textbook, I often find that I end up talking about things that aren't at all what you would find in the textbook, but are hopefully interesting and good ways to understand what's going on. So I'm perfectly happy to try and address those questions because I learn a bunch from them as well. All right, well, with that said, let's see, we have a number of questions saved up from last time, but please feel free to ask about any kind of science, physics, biology, any kind of mathematics, technology, computer technology, other kinds of technology. You may hit things I don't know about, but that if so, well, so it goes. But there'll probably be a bunch of stuff where I'll know things and might have something interesting, I hope, to say. All right, there was a question here saved up from before from Erin, asking, could you build a reverse natural language understanding engine, one that would take computer code and output natural language explaining what the code is doing? Okay, so first of all, let's talk about what the pieces of that mean. So by natural language, we mean languages like English and French and whatever that people speak. And one of the things that has been an achievement of recent times is the ability to understand natural language, to have computers understand natural language. And probably the most sophisticated such thing is our Wolfram Alpha knowledge engine that also does the computational knowledge for things like Siri and so on. But the point of Wolfram Alpha is to take something you ask in natural language, which is something like, what's the density of gold compared to lead, let's say, and you use English words to ask the question, and then its goal is to answer that question, perhaps to compute the answer. You know, what's the distance to the planet Jupiter right now? What's the distance between Jupiter and Saturn right now? That requires both understanding the question and being able to compute the answer to the question. So what Wolfram Alpha does is it takes the natural language that you've given it, and what it wants to do is to convert that natural language into a computational language where it can actually understand how to do the computations, where it has a sort of precise specification of what that language means. And part of the reason that we were able to build Wolfram Alpha, which came out in 2009, was that, and people have been trying to build kind of question answering systems as sort of exercises in artificial intelligence for many decades before that, and had not really gotten terribly far. The reason that we were able to do it was because we had another component that was huge and very critical, which was we already had a computational language into which these natural language questions could be turned. So when you say, what's the distance between Jupiter and Saturn, for example, we have a representation in our Wolfram language, computational language, of the planet Jupiter, the planet Saturn, the notion of their positions, the distance between them, the difference in distance, but difference in position between them and a distance between those things. We can represent that question in a computational language. So it might say, you know, entity, planet, Jupiter, and it might say something like, actually, I don't exactly know how to do this, but I think it would be that thing of, I don't know, position, and then that will give you a set of coordinates. Those coordinates are probably relative to the center of the sun, but then given those two sets of coordinates, you would be finding the Euclidean distance, let's say, between those planets, and that will give you some quantity, and then that's the answer. That's perhaps a more elaborate type of question, but the point is that all of those pieces, like in our Wolfram language, that's what makes it sort of a computational language instead of a programming language, is its ability to actually understand computationally things about the world, like the concept of the planet Jupiter, or things about positions of planets and so on, and to be able to deal with that as something that is intrinsic to the language, as opposed to a programming language where one's like C or Java or Python or something, where one is just dealing with things which a computer intrinsically knows about, that are to do with the actual structure of the computer and the intrinsic operations that a piece of computer hardware does, as opposed to things that are facts about the world or procedures for computing things in the world, which is the kind of thing that we've spent the last, well, 3 or 4 decades making happen, making work in our Wolfram language, computational language. But okay, so the thing with Wolfram Alpha is going from natural language to computational language. Once we have a question asked in computational language, then it's up to the implementation of the computational language and all the sources of data and algorithms and so on to be able to actually answer the question. And then we have another component of Wolfram Alpha, which is the ability to synthesize sort of a report that shows you the things you might want to know about the answer to that question. But the key piece is we're going from natural language into our computational language. And doing that is a whole collection of algorithms and whole collection of heuristics, kinds of ways to sort of guess things in an informed fashion that take sort of things about the structure of natural language and sort of break them apart and turn them into something that we can understand as part of our computational language. So for example, you might say, I don't know, let's take, simple example, something like, well, take the planet Jupiter. Okay, so I might say the planet Jupiter, or I might just say Jupiter. If I say Jupiter on its own, that might mean the town of Jupiter, Florida. It might mean some other, I'm sure there's companies and products named Jupiter, or it might mean the Roman god Jupiter. So we've got to be able to understand from the natural language of the word Jupiter, we've got to understand what it is. Maybe we said the planet Jupiter, or Jupiter the planet, or maybe we said but we can get a clue from kind of how we refer to Jupiter. We can also get a clue from other things we're asking about, like distance to Jupiter. Okay, well, that could be distance to Jupiter, Florida, or it could be distance to the planet Jupiter. By the time it's distance from Jupiter to Miami, well, that's probably Jupiter, Florida. If it's distance from Jupiter to Saturn, or distance from Jupiter to Earth, well, that's pretty certainly the planet. So these are the kinds of things, and in the natural language understanding that we do in Wolfram Alpha, it's kind of an elaborate set of ideas that have to do with, for example, different probabilities of different things that might be what one's talking about. Usually those probabilities resolve very, very quickly. Usually by the time there's a decent number of words in the natural language, one has really nailed, is it Jupiter, Florida, or Jupiter the planet, or Jupiter the god, and so on. But in any case, so that's the process of going from natural language to computational language. Now, the question that was being asked here was a different question, which is, if you've got a piece of code, maybe it's programming language code, maybe it's computational language code. If you've got a piece of code, then can you explain in natural language what that code is doing? Okay, so having spent a large part of my life as a designer of computational language, I would say, if you need to explain it, that's a sign that your language was not designed correctly. So for example, if you have something where you've got a piece of, I don't know, C code for I equals 0, I less than 10, I plus plus, J equals I times I or something. Let's say that's the piece of code. Now, I might explain that piece of code by annotating it. Oh, I plus plus means increment I after this happens, or this for loop has a test that does this or that. That's perhaps not a good example because it's comparatively simple, but the issue is a language that is, the goal of a language designer is to make this bridge between what humans readily understand and what is precisely specified in a way that computers can do something with it. And if you do something where humans can't readily understand it, you're not doing good language design. You can say, as people often do, oh, but I want to set up the language that way because it makes it easier for the computer. And in the early days of programming languages back in the late 1950s, early 1960s, that was an important thing. Computer time was vastly more expensive than programmer time. And it was really important to kind of optimize what the computer did over all of that effort the programmer might have to spend to figure out how to write the right program. Well, that has long ago flipped around dramatically. And what's relevant now is, can the programmer understand what to do? Can they do it correctly? Can they write a program that is likely to do what they want? As opposed to, the program will always do what the program does. The question is, does the program do what you had in mind to want the program to do? Because if you write the program and the program doesn't do what you thought it should do, then you'll say, well, my program has a bug. But the program does what the program was written down to do, so to speak. The program, it's just that what you wrote the program down to do isn't what you thought about having the program do, so to speak. So I think the main point is that when you are trying to write a program, the goal is to have a language in which you can, as directly as possible, take things the way you think about them and write them down so that you can have the computer execute them. And so one of the issues is, if you are dealing with a very low-level language, that is a language very close to the raw operations of the computer doesn't even know about something like the for loop that I mentioned from the C programming language. It knows about things like set this value in this register in the CPU of the computer, move this data from here to here, take the data from this memory location and that memory location and add these together. That's what the computer intrinsically knows about. And the lowest level that you can program a computer is its machine code, where you're just saying there are a certain set of operations that the computer intrinsically knows how to do, maybe 100 of them, like adding things, moving data from memory. And the level of machine code, you're saying opcode number 37. Use that, operate on memory location numbered such and such, and memory and register number such and such. That's what the raw machine code of the computer looks like. Then you get to assembly language, where you start to be able to have names for things. And then you get to the low-level languages like C and so on, where you have where you can use things like where you can have a slightly more sort of human readable version of the specification of what the computer is doing. But in the end, it's fairly direct to go from C code to what is actually the machine code of the computer. It's a fairly direct process of compiling it. You just take the C program and you're converting it down to machine code, so to speak. These days, usually through a couple of intermediate levels. But in any case, and so in a sense, the way computers are set up, they're set up to work the way they work. They with some effort to sort of pander to the humans, but mostly they're set up to work the way they work, to be as efficient as possible, to take the kinds of computations, to be efficient in running through different kinds of computations, and to be something that can be readily implemented in computer hardware. And one should not forget, there is a certain tradition and history to the way that computers get set up, which really hasn't changed much in more than 50 years now. And there's a whole sort of chain of technology, of compilers and all these kinds of things that are all built on top of a certain set of assumptions about how computers are intrinsically constructed and how the operations in computer CPUs work. That's why, for example, if somebody says, well, we're going to introduce new kinds of computer operations, that's a huge kind of issue of building the sort of a whole depth of tooling for computers to be able to deal with that. Well, in any case, so when we're dealing with languages so a language like C is a pretty well-designed language for what it is, which is kind of a wrapper around the intrinsic operations of the machine. And those wrappers get a little thicker. So a big issue is memory management. When you have if you are going to say, I've got an array of data, let's say a list of numbers, and it's of length 1,000 or something, and you say, I want to store that in the memory of the computer. Okay, you've got to allocate 1,000 elements of memory to store that array. Okay, well, maybe you stop using that array sometime. So you've got to say, okay, I don't need to use those 1,000 elements of memory anymore. Let's give them back to the operating system and let another part of my program or another program altogether make use of those elements of memory. And so the process of like managing memory like that, of saying, oh, I'm using this thing, I've stopped using it, et cetera, et cetera, et cetera, something like the C programming language basically doesn't do any of that. Well, it does a little bit of it when you're calling functions. It has this notion of the function stack where that happens. But when you're allocating memory to just work with it, it doesn't do those kinds of things. One of the sort of innovations of slightly higher level languages is that they have various ways of somewhat automatically dealing with the allocation and deallocation of memory. When you're using Wolfram Language, for example, you never would see anything about memory allocation and deallocation. That's many, many, many layers below what an actual human user is exposed to. And just not a thing that comes up. And so the thing that when you're talking about taking a piece of programming language code, it might contain things about memory allocation. It might contain all kinds of things representing different kinds of data structures, of saying, how do you represent this two-dimensional array? Is it a list of one-dimensional array elements? Is it something which is indexed into with two variables or with one combined in a sort of in a positional notation kind of thing? You know, how does that all work? And that's all, a lot of that tends to be explicitly exposed in typical programming languages. So the question then is, if you've got a piece of programming language code, it may be hard to understand. And you might say, well, let's annotate it by giving natural language and sort of making, sort of automatically generating comments about what the code is doing. Well, the goal of something like Wolfram Language is to not have that make any sense, to have it be the case that what you write in the actual computational language itself is the clearest expression that you can give of what you want to do. And anything you might give saying, this is doing this, that's doing that, is going to be largely irrelevant. And when it's a question of saying, often it's useful in understanding a piece of code to sort of think of it in a modular way. Say, this piece is doing this piece is doing this, now you fit them together. that's the way that we will typically explain and talk about things. We don't just have a sentence that's, I don't know, we don't have a 400-word sentence. That will be very, very hard to understand with lots of subclauses and so on. Some philosophers of the past particularly were fond of writing these monumentally long sentences, which are extremely hard to understand. We tend to break things up into smaller sentences, paragraphs, things like that, because our brains seem to do much better at processing things when they're sort of presented in this modular, hierarchical kind of way. And it's the same kind of thing with programming language and computational language, that it's typically useful to break things up. And one does that by writing lots of little functions, and one gives those functions names. And those names are a very important clue for us humans about what's going on. It's like we could say, I mentioned the sort of the machine code of a computer might be opcode number 37, opcode number 38. But those things are, add, multiply. As soon as you call them add and multiply, it's like, oh yeah, I know what that is. It would be like if I were talking in English, in natural language, and instead of naming things, instead of saying, an elephant and a turtle, I would say species number 642, species number 875. It would be super difficult for us to understand that, because the way that our brains are set up, we use things like words and nouns and so on as kind of keys into just this whole kind of bundle of knowledge that we have about these different kinds of things. So when you're writing a program, one of the things that is quite important is try to come up with sort of names for the functions you use. First of all, make your program out of lots of little separate functions, and then name those functions according to the thing that you will want to think about, that is a description of what that function is doing. Now, one of the classics of programming is essentially all languages have this notion of comments. You're writing your code and you can put a comment, something which will be ignored by the computer, but it's just intended for a human who's reading that piece of code. So, in Wolfram Language, it'll be paren star, and then you have some piece of text that is your comment, and you end it with a star paren, and that's a and when the Wolfram Language system comes to look at that piece of code, it's just going to say, I don't care about that. That's only for the humans. Okay. Now, the classic thing about programming language, about coding and software engineering, is people write a big lump of code and they'll write a comment. The code will be correct, but the comment will be misleading and perhaps wrong. And in a sense, writing comments is its own kind of exercise in programming, writing comments, but usually people don't take the comments as seriously as they take their code. And so it's really common for comments to be extremely misleading and even simply incorrect. I might say that in this kind of thing about how you write code, one of the other areas, happens to be something I'm thinking about right now, is you write a piece of code that is intended to do what you intend it to do. But there might be some error case. It might be that, I don't know, you're trying to figure out, I don't know, population density of animals based on certain data, but the animal is not aquatic, and in the ocean it should be 0. And something goes wrong in that case. And it's sort of a corner case you didn't think of. And it's, I just didn't think of the case where the animal can't live there because it's an ocean type thing, whatever else, in writing your code. That's sort of an error case that's not part of the main, the main kind of code path that you're using. And error cases will be less thought about than the main code path, because the main code path is what you expect the program mostly to do. And so the error case is something where you kind of need a net to catch what happens if you go into the error case, but you're not going to spend all that effort to deal with the error case because it's an unusual corner case that you think isn't going to happen. So it's the thing that the thing that happens is people put less effort into this kind of into writing the what happens in the error case than they do in the what happens in the standard code path. One of the things I always find amusing is you'll see messages that people write for errors. And one of the ones that comes up from time to time in programs people write is it'll say something like impossible error, like it printed it out. It's like it's possible, it knows it's possible to print it out, but it's basically saying this error cannot happen. What does that mean? It means the programmer could not imagine a case in which this error could happen, but actually it just did happen. You got to see it. It reminds me, I have to tell a little bit of a story from a long time ago in the 1970s when I was using a big mainframe computer the size of a large room that you program with punch cards and things like that. And it was a big IBM mainframe computer. And I run this program and it got some error. And usually in those days, the errors were given designations like, IEH 2036 or something. The error didn't tell you what the error actually was. It just said, IEH 3026 or something. And so to find out what the error was, you had to look through these big, shelf-sized documentation for the error. And so I did that for some error that I got. And there were pages and pages of errors. And I finally get to the error that was the error that I had got. And the only explanation for the error was probable user error. So that's like totally useless. What was going on? The point was the vast majority of those errors were things that could go wrong with the computer as a piece of computer hardware, not something we see much today. And the case of, it was the programmer who made a mistake. That was kind of like, that's that we don't have to worry about that case. The cases of interest that were mostly documented were things that could go wrong with the computer. Anyway, things have changed since then. But now the question is, can we generate, the original question here is, can we go from a piece of programming language code to an explanation of what this code is doing? I would say my number one answer to how to do that is write your code in Wolfram Language instead. Then you will have something where the language was actually designed to be able to explain what the code was doing. If you're writing in a low-level language, which was mostly for the benefit of the computer, then it's not surprising the human can't understand it. Now, having said that, there are things like, for example, can you automatically generate a reasonable name for a function? We've done lots of experiments on this using machine learning, trying to learn from existing code corpora, things like this. It's really hard. That's something humans are decent at, but it's really hard to do that automatically. So actually, humans are not that good at it. Humans often do a surprisingly bad job, actually, coming up with reasonable names for their functions, because they have in their mind the thing they were thinking about at the moment they wrote the function, which was one kind of use of that function. They don't have in mind some other use. They kind of, their thinking has been dragged in some particular direction and they're not thinking more broadly. Another case is, could you automatically generate a reasonable message saying what went wrong in this piece of code? That's a little closer to being possible, I think. And we've been doing a bunch of experiments on that. There are a thing that is much more possible is when you type in the code, can you guess whether this is a reasonably likely piece of code for somebody to want to type in? And that's something where you can use information on sort of the statistics of what people typically write in code like this to be able to guess that. It's much like spell checking. In principle, you might want to spell some word in some totally funky way because it's a new use of that word, but chances are you don't want to do that. And so the spell checker is telling you that. And so I think that's a kind of thing which one can do. The other thing that I've been very interested in is the question of, if you run a piece of code and it gives the wrong answer, can you synthesize an explanation for why the answer was the way it was, given that you told it, I really should have got 11, but the code actually gave 96 or something. You say it was supposed to be 11. And the question is, can you ever figure out, can you try to figure out how would it have gotten to 11? What did you get wrong? An important thing to notice in another thing we've been interested in is code simplification. You write a piece of code and it's got all kinds of little pieces in it and so on. And you say, simplify this piece of code. Like you might say, if you have an algebraic expression and you have the expression, I don't know, x plus 1 times x minus 2 times x plus 3 times whatever, you might say, can you simplify that, or maybe divided by a bunch of things? Can you simplify it? Oh, yes, I can do an algebraic transformation, and the answer is x cubed minus 3 or something. And so I take this big, long algebraic expression, and that's equal to x cubed minus 3, and I can discover that by doing mathematical transformations. So the question is, can you do the same kind of thing with computer code? Say, well, you, the programmer, wrote this as a 10-line piece of code, but actually there's a way to rearrange it so that it's only 2 lines long. And if one's lucky, it's 2 lines that really explain what the point is much more clearly. They really are like a good piece of exposition in English. They are explaining the point in a way that's clear, so that then you will understand what's going on, and maybe the code will even run more efficiently. I should have said, by the way, in terms of this question of what does the code do, that you can write code in a kind of sloppy way, just as you can write English in a sloppy way, and it's really pretty hard to understand. You know, I could invent, as I'm trying to explain things to you all, you know, part of what I try to do is structure the explanation in a certain way, like say the main point, explain the point, et cetera, et cetera, et cetera. It's not hard to end up in a situation where you are not explaining things in a way that has that kind of structure, and where it's really hard to understand what's going on. Let me give you an example that comes up in Wolfram Alpha, actually, and in Siri and so on. Let's say I ask, what's the population of New York City? And the answer is something like 18,726,344. And that's the answer. Now, that answer is actually, when you just hear that, or maybe we can even make it more complicated and have a string of numbers that come out, that answer is probably not the easiest to understand answer. A better answer would be, the population is about 18 million, or more exactly, blah, 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 you know, and then maybe there are additional footnotes like based on the previous census data, blah, blah, blah. But saying it's roughly 18 million or more exactly, blah, 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 is a much more human, absorbable explanation than let's just jump right into the details and go start saying the details right up front. And that's, you know, characteristic of expository writing, is that you have to have some of these kind of structural elements to help people understand things. You know, one of the things that I could yak on about this for ages about expository writing, because I've done quite a lot of it in my life. You know, one of the things when you're writing things like documentation for computational kinds of things, and there's some other places where this happens as well, is, for example, there may be a main point, the critical point. If the critical point is said in 4 words, even if those words are really clear, halfway down the page, nobody's going to notice. You kind of have to, you know, one of my theories of computer documentation is the importance of a point should be roughly proportional to the actual area it takes up on the page of talking about it. So if the point is important, you've got to find ways to kind of puff it up so people really notice that that point is being made, rather than just, oh, it's in those 4 words that are really clear, but you probably missed them. And similarly, it's important sometimes as you explain things to be able to say, to make meta comments like, this is the really important point, or this is a detailed point and you don't really need to, it's kind of like a detail. It's important to signpost those kinds of things because that's important for exposition. Now, when you're presenting a piece of code, the question is, can you sort of simplify code to make it more expositorily, more clear in its exposition? And the answer is you can do some of that. And one of the things you find if you do program simplification is very hard. It's a very hard thing to do, but you can do at least certain cases of it. One of the things you find is somebody writes a piece of code and you try and simplify it. You do it in Wolfram Language, and you'll find, well, the simplified piece of code is mostly just this one function that says, you know, reverse the transpose of this thing or whatever it is. But then it's got a little extra case hanging off the end. If blah, blah, blah is less than this, then do this thing. And that's the extra case that hangs off the end. So it's mostly just there's this very simple thing with a couple of functions, but then there are these special cases hanging off the end. Okay, in a well-designed computational language, it's probably the case that those special cases are bugs, that they're things the programmer didn't think of, but they're things where the design, the intrinsic design of the language would do what you actually want to do, and you have to special case those things where you're doing something different from what the language thought you wanted to do. So that's, in a sense, it's a great way to find bugs, is you simplify the program, and if you've got weird little extra pieces hanging off the end, those are things you need to look at very carefully because they're corner cases that you probably didn't get right. So in any case, I think that this kind of effort of can you create a something where you can, given that you run a piece of code, you get the wrong answer, you know, can you kind of say, why is it that answer not the one I expected? I think it is possible in the next few years that we will be able to do some of that. And in what language would you express the why did it go wrong? That's an interesting question. For example, when you give a mathematical proof, there's a question of how do you give the proof? There might be a mathematical result that, you know, this particular, the prime number, you know, you know, 2 to the prime number of this is always equal to this. That might be the result, and you might be able to express that result quite easily in mathematical notation. But the proof of that result is something that on its face is not expressible in mathematical notation. Instead, the proof will be an explanation that might be a mixture of things in English and some math and et cetera, et cetera, et cetera. So the representation of a proof is already a difficult thing. And we've been interested in that actually for a very long time in Wolfram Language. And we finally had, there's a function called find equational proof, which generates a kind of structure that represents a proof. But we're not super happy with it. Now, actually, this process of representing a proof is like, it's like representing the intermediate steps of a computation. And for example, in our model of physics, all of the things we're experiencing in the world, in physics, and the progress of time are just like intermediate steps of the big computation that is the one being done by our universe. So in a sense, what we experience is exactly the innards of a computation being done. But the general question when we've described the computation, most of what we want to do in Wolfram Language is, here's a question, get me the answer. Here's the input, crunch, 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 get the output. Representing the intermediate steps is an interesting problem. That's a completely unsolved problem. It's a problem that's not even been solved for low-level programming languages, let alone a sophisticated computational language like ours. And in fact, perhaps it will be easier because in our computational language, it is our goal to represent everything, and representing the progress of a computation is part of the story of everything, so to speak. And in fact, we have, I mean, I make it sound like we don't have anything figured out about this. Actually, quite recently, we've been working on this and trying to use ideas from our physics project to represent kind of the progress of computations, the way that sort of events happen in computations, and what that sort of flow of data is through the computation. So that's a sort of a coming attraction, but we don't yet have a good language to describe sort of what happens inside a program. And so I suppose that's sort of a prerequisite for describing an actual program running. We can say, this is the program, but now we run the program, and the program is going to do a lot of things internally. We don't have a great way to represent that sort of space-time diagram of the running of the program. We can say, here is the program, here is the input, here's the output, but the actual sort of progress of the program, we don't have a great way to represent that, and that's something we're working on. I think that then the question of the why did my program do the wrong thing ends up being, why did you get this space-time diagram, basically, rather than that one? And perhaps that's the way to think about sort of the process of seeing what's wrong. I mean, it's a little bit like sometimes the wrong answers, well, in human computation, wrong answers usually give you a lot more information than right answers. So for example, I don't know, somebody does an arithmetic problem, they're doing long multiplication of two numbers and they get the right answer. Okay, great. They got the right answer. There could be many methods by which they got that answer. It's all good. Let's say they get the wrong answer. Well, there are many, many wrong answers you could have given. Let's say it's a 5-digit number. There are, a million wrong answers that you could have given in addition to the single right answer. So if you look at the wrong answer, you can quite possibly backtrack to figure out, well, what did they do wrong? Did they miscopy a 4 for a 9 or something somewhere in the intermediate stages? You can actually figure out, we did a little project on this at one time, you can actually do for like addition and multiplication, you can actually do a pretty decent job usually, given the wrong answer, of backtracking to find out what did the person do wrong. And then, so that's sort of an example of something a little bit like the computational case, although it's in a more limited domain of things. All right, long answer there. Okay, we've got a bunch of other questions here. Let's see. All right. There's a question here from Golagaz. Suggestions on problems and cases to use for introductory programming. Well, I mean, I've spent the last 40 years basically building our Wolfram Language computational language system, which is, I mean, I would like to say it's a computational language, but it is the world's only full-scale computational language. And that's sort of 40 years of work that's got it to that point. And nothing else has really been building in that direction. So it would be much easier if I could just say a computational language, like all the other ones that you already know about, but I can't say that. But kind of the goal with Wolfram Language, as I mentioned, is to be able to have a way to describe things in the world computationally. And when people want to use computers, that's what they ultimately want to do, is they want to be able to deal with things in the world computationally, so to speak. It could be in the abstract world, but they want to be able to deal with things they care about computationally. And the sort of traditional view of low-level programming, which is the one that came from sort of the early days of computing from 60 years ago and so on, is let's learn how to write things that are precisely how the computer works. It's like, let's not learn to drive a car by pressing the gas pedal and driving the steering wheel. Let's learn how to actually pump things into the carburetor and do the have fuel go into the cylinders and things like that. We don't need to know that stuff anymore for computers. It is many layers below what you actually need to know. It might be interesting, you might care about it, it's something to study, but it's not something, if you are wanting to use computation to do things, it's just not stuff you need to know about. So in terms of what you can do to learn about computation, I wrote a little book called Elementary Introduction to Wolfram Language, which you can find on the web, and you can find MOOCs around it and things like that. I would suspect that well, the demographic for people watching this and people for whom my Elementary Introduction book is relevant is probably an intersecting demographic, at least. I wrote that Elementary Introduction book to be suitable for high school students and others. It's been used a lot by the others as well, but it's intended for those kinds of folk, and it's kind of it tries to explain how to do computation for dealing with images or sounds or maps or just arrays of numbers or whatever else. And that's a good place to start. And then it's just take something that you think is interesting in the world, whether it's some data from the world, whether it's some operation you want to do, so to speak, and think, how do I represent that computationally? And then if I and we did a good job designing Wolfram Language, then that's something you should be able to rather directly use in our language. And the Elementary Introduction book should get you to the point where you're able to do that for a pretty wide class of things, or at least able to know the principles by which you can do that. usually the difficult part is to take what you're thinking about and know how to think about it computationally so that you can feed it to the computational language. But that's a part that is sort of the human step. That's a part where us humans are the ones that really have to do that, because we're the ones who know what we want to do. And that's the part to learn. But the pure skill aspect of knowing, given that I've conceptualized something computationally, how do I actually get it to the computer? Well, for example, my elementary introduction book is probably a good bridge for that piece. Let's see, well, we got a math question here from Gist. Why is it harder to compute integrals than derivatives? Well, this is one of these cases where if I sort of broke my rule of just talking to you guys and started actually typing something on a computer, it might be a little easier, but I'll see what I can do just talking about this. So just a little bit of a refresher for people on derivatives and integrals in general. It's what one's doing is one has some function, f of x. So what does that mean? Well, it means, f of x could be, I don't know, let's say it could be I'm trying, well, okay, the most obvious thing is it's f of t, where t is time, and f represents the position of a thing as a function of time. So something is moving around as a function of time, and you can draw that as a curve where the distance it goes is, it goes forwards, it goes backwards, et cetera, et cetera, et cetera. And the derivative is the slope of that curve, which means in the case of something moving, where the curve is representing position as a function of time, the derivative is the velocity, the speed of the thing. It's the rate of change of position with time. That's the first derivative of this function, sometimes written f prime of t, f dot, sometimes written df of t divided by dt. That's a very confusing notation invented by Leibniz in the late 1600s, where even he knew the day he invented it that it was a confusing notation, but it's still with us 300 and something years later. In any case, so derivative is the slope of the function, the rate of change of the function. The integral is the area under the curve. In some fields, like in medicine, for example, what is in mathematics usually called the integral is usually called AUC, the area under the curve, and that will tell you if what we were plotting was instead the velocity, then the area under the curve would give us the position. And so one of the points about integrals and derivatives is they're basically inverses of each other. If you know the area under the curve, the rate of change of the area under the curve is the actual position of the original curve. And that's true up to a constant where, because you could have said, well, the area under the curve includes all the stuff to the left, but that's not relevant for working. When you work out the slope of that, you're dropping that piece. But so the basic concept is the derivative is working out the slope, the integral is working out the area, and they're inverses of each other in the sense that the derivative of an integral is equal to the thing you started from. The integral of the derivative is the thing you started from up to some constants. Okay, so given that description, why would it be harder to work out the derivative, work out the integral, than work out the derivative? The reason is that when you write down mathematical expressions, the story is different. There are tricks for working out derivatives, and the most important trick is a thing called the chain rule. And basically the point is this: if you have some function g of t, and you say f of g of t, so that means you compute g of t, and then you can take the result of that and you compute f of that. Okay, so it then turns out that if you want to find the rate of change of f of g of t, then that can be broken. Gosh, I haven't thought about this by hand in a million years. I feel like I have to type this into Wolfram Language if I'm going to actually know the right answer. But basically what happens is that that thing, I feel like I have to type this in, otherwise I'm literally going to tell you the wrong thing, because I never think about this by hand. It's when I have to say, one of those unendearing things when you see a kid doing their calculus homework, you say, I didn't think humans still did that kind of thing. But anyway, so anyway, what happens, the chain rule, so f of g of x, essentially you can break apart the change of g and the change of f. And so the change of the whole thing is f prime. I'm reading it off the screen now because to make sure I know this one, but f prime of g of t times g prime of t. So in other words, the sort of the final answer is the rate of change of each nested piece multiplied together. So the reason derivatives are easier to work out is because you can take apart any mathematical expression. You can think about it as kind of a nested collection of functions. It's like and in fact, in Wolfram language, if you say, what's x cubed times 1 plus x or something, that will be the times of power of x comma 3 comma, and then the plus of whatever I said, 1 and x. So so it's represented, even at the any mathematical expression is represented as this kind of tree structured thing. And then the derivative can always be gotten by just using the chain rule. That's this rule which says the derivative of this nested collection of functions is the product of essentially the changes of the individual functions separated. So it's a very systematic procedure that lets you take this mathematical expression represented, a symbolic mathematical expression represented in this kind of tree-like form of functions of functions of functions, and then you take the derivative, and all those individual functions have their changings that they're doing, and what the results you get are essentially based on products of those individual changes. Okay, that's how it works for derivatives. For integrals, no such thing is true. The integral of something is sort of a puzzle where you have to say, well, let me figure it out so that I get the right derivative. But there's no systematic procedure like the chain rule for finding integrals. Well, that's more or less true. It's not, at a sophisticated level, it isn't quite true. So when you find the integral, there are rules, like the integral of, I don't know, x to the power n is x to the power n plus 1 divided by n plus 1. That's just a rule, and there are lots of other such rules that one knows. But the problem is that, unlike for derivatives, where once you know one of those rules, you can use it for that individual part of the expression, and the thing you get for the whole expression is just sort of the nesting of all those rules. There's no such similar sort of rule of combination for integrals. Well, there's a integration by parts is sort of a little bit like that, but it doesn't work in the same kind of everything falls apart kind of way. It's just a rather specific thing for products of two elements. So it's and the other thing that happens is, when you're doing derivatives, because you can look at each part separately, it's kind of a limit to how complicated things can get. In the case of an integral, because it's sort of everything together, you sometimes can get these very elaborate, ornate, complicated functions, which are the solution to that puzzle of what do you need to produce that whose derivative will be the original thing you started from. And so that there's sort of one of the things about doing integrals is, if you can guess what the general form of the integral is, oh, I know that will be a log integral function multiplied by some logarithms with some powers of x and so on. If you know that general form, you have a fighting chance, because you can just find that general form, fill in parameters, a, b, c, d, for I don't know which power it is, I don't know how many of these there are, et cetera, et cetera, et cetera. I know it's of this form. You take that general form, you find the derivative, which is straightforward to do, which also will involve those parameters. You say, is there a way of matching up those parameters so that it will agree with what I had as the thing I was trying to do as an integral? I have to say, when I used to do integrals by hand, back, 40 something years ago, before I switched to always doing them with computers. That must have been 1977 that I made that switch. That's why I get to have to type in the chain rule, because I'm not sure I remember it exactly right. But in any case, the thing that people, when they learn to do integrals by hand, they often learn all of these tricks for, I don't know, I don't even remember what these tricks are, trig substitutions, all sorts of tricks. And those tricks tend to be, it's sort of a pattern matching thing to figure out what trick can I use in this case. This idea of guess the general form of the integral and then match it up is a pretty good general trick, which I don't think they ever teach to people, but it's a really good thing. If you're actually confronted with, here's an integral you have to do, if you can guess the general form. By the way, in modern times, there's the potential for machine learning to be a useful way to try and guess general forms like that. I should say that when one actually does integrals sort of for real, so to speak, one of the things, like in Wolfram Language, the way we do integrals is we actually convert things to much more sophisticated mathematical functions. So you have an integral that's involving sine and logarithm functions and so on. We convert that to an integral involving things called Mayer G functions, usually, which are some very generalized kinds of mathematical functions. And given that it's converted, the integrand is converted into that form, there's a very general way that you can do integrals of all such functions. And then the real challenge is, can you take the answer you get and turn it into something that is recognizable by humans as mathematical functions they would want, so to speak. And that ends up being the main challenge. But it's a very typical thing in doing integrals that you start off with a very simple function, like, I don't know, what's a good example? Integral of log 1 plus x over x. What is that? Well, you might say, oh, surely I can do that integral. I must have learned how to do that integral in elementary calculus class. Well, actually, no, that integral comes out in terms of a thing called the dilogarithm function, which they never talk about in elementary calculus classes. And it's very easy to go from something like that to something where it's a very complicated function, or a different, you're in a new kind of class of functions. Classic example of this, well, the integral of sine x is sine x is cos x, but the integral of sine of x is really difficult, and that comes out. I think we can now finally, after 30-something years, that's an integral we can finally do, and it comes out in terms of a Pell F1 function, which is a generalized multivariate hypergeometric function. It's a really complicated story. But what happens with integrals is this whole thing of there may not be a way. Okay, so I should explain, it's not even obvious that there will be a function that has a name that anybody's ever talked about before that would be the thing that represents the integral of sine of x. It could be that this integral just can't be done in terms of the class of functions you know about. Yes, there is, if you were just working out the numbers of what is the area under this curve up to some point, yes, you can absolutely figure that out, the numerical integral. But to represent it in symbolic form as a formula, there may not be a formula that is in terms of functions you already know about that represents that integral. Well, let's see. Question here from Spicy. Are there major changes to the design architecture or low-level code of computers that are standard now that I would change if I could? Well, okay, there's a couple of things to say about that. First thing is that once you have a universal computer, a computer that is programmable, you can program it to do anything, or anything for which you can program anything to do it. And so in a sense, however crazy the machine code of a computer is, by the time you're building layers of software on top of it, eventually you can get to a layer of software where it doesn't really matter what was underneath, because the layer of software, the computational language, let's say, that you have, is optimized for the humans, in a way that they just don't see all that weird stuff that was underneath in the weird and wacky choice of opcodes in the machine code or whatever else. So that's kind of the most basic thing to say. Now, having said that, sometimes the architecture can be such that the speed of doing things is just way too slow if you build those layers of software and you really rely on having something built into the hardware of the computer that does something efficiently. So there are a number of things where I think, things have been done wrong. A classic is the thing called the IEEE floating point standard, which I think has probably caused more kind of bad things to happen in the world than any other single computer architecture idea. But so let me explain what that is. So if you take a number on a computer and it's the number 3.782645, whatever it is. No, let's just take the number, let's say 1/3, 1 divided by 3. Okay. In Wolfram Language, for example, you can just deal with the rational number 1 divided by 3. You multiply it by 3, you get exactly 1. Okay. In a typical sort of low-level computer system, you would use a so-called floating point number to represent 1/3. What is that number? It's 0.33333333, and the official mathematical number is 0.33333 with the 3's going on forever. But in a computer, you can only have a certain limited amount of memory in which to store that number. And so the most common thing is to use 64 binary bits. So to represent that number is 0.33333 with about 16 3's there, and that's all you get. Okay, so then the big question is, well, what do you do if you've got the 16 3's, you know roughly what the number is, but there's some error. There are many numbers that could have their further digits could be different, but they're all represented by your 0.333 16 times number. But after that, it could go on 333, or it could go 678 145, et cetera, et cetera, et cetera. There are many different numbers that are consistent with being the same up to the digits that you've actually stored in the computer. Okay, so the question then is, what do you do with those digits you don't know? Well, let's say you take that number, the 0.333, whatever number, you multiply it by 3. Do you get 1? Well, no, you won't get exactly 1, because you get 1, but there's a potential error in the value of 1, so to speak, because it could have been you had 0.333, let's just say it was 4 digits that were being stored, 0.333, no, let's say 3 digits, 0.333. And then it could be after that, it was 0 after that, or it could be 0.333999999 after that. Okay, so depending on which of those it is, you'll get a different answer when you multiply by 3, and let's say you multiply by 3 and subtract 1, you'll be seeing only those digits that were cut off when you stored them in the computer. Okay, so the question is, what do you do in that case? And the issue is, do you give the user any indication that you are having to essentially excavate digits that weren't there? And in the case that I just described, where you multiply by 3 and subtract 1, that is essentially giving you precisely digits that are unknown. But in the standard way computers are set up, with the so-called IEEE floating point standard, you never know that. Unless you've built sort of a harness in your software that carefully figures that out, unless you built that harness, the computer just says, oh, the answer is 2, let's say. And that's all you know. And the fact that that 2 or that 0.2, let's say, came from digits that just weren't there. They were just excavated from nothing. The particular digit that came out depended on the actual way that the arithmetic was done inside the computer, and it was using this thing and it was shifting bits from this place and so on. The actual number that came out is complete nonsense. Every digit in it is nonsense, but you don't know that. And so that's the way that computers are set up right now, is when they deal with these real numbers, these floating point numbers. They're called floating point because the decimal point, the number is actually ultimately represented as, let's say it's 333.3. That will be represented as 3.33333 times 10 to the power 2. Well, actually, it's in binary, so it's times 2 to the whatever. But it's roughly that. So that's why it's called floating point, is because the decimal point is you're specifying separately where the decimal point floats to within the number. The number is just its digits, and then you're separately saying where the decimal point is. Okay, so the issue is that in the current way things are set up, you don't know whether the digits that you got given, you're always given, let's say you're using standard 64-bit floating point arithmetic, you're always given essentially 16 digits back. The answer is always 16 digits long. Now, are those 16 digits correct or not? You have no idea. And sometimes the computer could readily have known that those digits are definitely garbage. Now, in Wolfram Language, we have a mechanism for tracking the precision of numbers. So, for example, if you ended up with something where all the digits you've got would be garbage, it will just tell you that's a number of no precision. It's a number where there are no digits known. It'll make a little pink box or something. It'll say 0 times 10 to the times 10 to the 4 or something, means there's no digit known up to that position. But the tracking of precision like that is something that takes more computational operations, because it's not something built into the hardware of computers. It could be, but it isn't. This decision was made in the late 60s, early 70s. And actually, I've certainly met the person who was responsible for pushing that decision. And I will say that, you know, this is the way technology history tends to work, is, you know, I'm like, this seems like, you know, this is not a good idea. And it's like, well, but you can do numerical analysis. You can study the algorithm that you're using, and you can find out that it's not going to generate the wrong digits. Well, this particular individual spent his career as a professor of numerical analysis. So yes, it's good for his business to say, everybody who uses a computer and uses floating point numbers on a computer, go learn numerical analysis and go analyze all your algorithms to find out if they're going to generate sort of bad numerical precision kinds of things. Well, of course, nobody does that. And so actually what happens is people just get wrong answers, and they write down their, you know, the answer is 6.78462. Actually, all those digits are garbage. And the computer and in Wolfram Language, when you use our arbitrary precision arithmetic mechanism, you'll find out, yes, we know those digits are garbage, and we won't show them to you. We'll only show you the digits that can be justified on the basis of the actual computation that you did. So that's an example of something which I think is one of those burnt-in horrors that really is not fixable at this point, and you just have to sort of paper over it. I would say that the other big issue in terms of the way computers work, well, I mean, there are completely different models of how computation happens, but I don't think it's that important, because you can build those models on top of sort of the existing low-level computer operations. That's not really a difficult thing to do. I think that the one sort of big area is sequential versus parallel operations. That is, does a computer just say, I'll do this, then this, then this, then this, or can it do many operations in parallel? And increasingly, modern CPUs can deal with multi-threading and can deal with having different sort of different streams of instructions being executed together. GPUs can do much more along those lines. Well, and they deal with array operations where you're doing something on every element of a collection of numbers at the same time. The difficulty with parallel programming is the programming part. In other words, we humans tend to think very sequentially. We have a certain thread of experience that we go through. We think of time as being this kind of one-dimensional thing where this happens, then this happens, then this happens. And this case where everything's happening at the same time, that's something we're not as familiar with. I mean, we can see in space, for example, things can be laid out in space, and at different places in space, different things can happen at the same time. But it's much harder for us to understand what's going on when multiple things are happening and all interacting with each other than when there's this single thread of experience, single thread of time. And I think it's sort of a fundamental feature of the way our consciousness works, that we are used to experiencing things in this kind of single thread of time. So when we write programs, we tend to really have a need to sequentialize things like that. And people have, for 50 years, had sort of experiments on making parallel processing kinds of computers where many things can happen at once. the real bottleneck there is for us humans to understand how to program that. And actually, this is something I'm actively working on right now, partly because in the last year or so, we've kind of understood on the basis of our approach to fundamental physics, this kind of new way to think about what I call multi-computation, the sort of multi-computational paradigm, which has to do with having multiple threads of time rather than just a single thread of time, having multiple threads of time and knowing what kind of the aggregate effect of having multiple threads of time is. And that turns out to be something deeply related to our experience of physics. And one can, I think, maybe leverage that experience of physics that we have to let us be able to think about things in terms of writing programs in ways that we haven't been able to do before. I mean, in a sense, a lot of the way that we do programming today is based on the metaphor of kind of the way that we explain things to other people. It's very sequential. It's very do this, then that kind of thing. We try in Wolfram Language, for example, a lot of what's going on there is something that really leverages the human ability to kind of think about things symbolically, to have this sort of thing that is kind of the description of something, and then you can take that description and apply something to that description and so on. This is kind of the idea of sort of symbolic functional programming is all about doing things like that. And that's a very good metaphor to leverage in thinking about how to specify programs. So it is possible that the metaphors that we have from physics will be useful in being able to write programs too. And that's something where, because we are used to things happening in parallel, different places in space at the same time, that we may be able to leverage that to be able to more easily have a way to write programs that work in parallel. Now, but by the way, I mean, one piece of that is already a solved problem, which is an operation on an array of numbers. Let's say you have this whole list of numbers, you want to add one to everything. Okay, we understand pretty easily how to do that, and it's really easy in Wolfram Language to do that. It's just you've got the list of numbers, and you say +1, it'll add 1 to every number. That's a cognitively easy thing for us to do. But if I now told you each one of those numbers, I'm going to do this operation and different things could happen with different numbers and they're going to be combined together, then it's pretty difficult. Usually it's difficult to have a way to think about that. So it's something where we're trying to figure out what is the right way to, what is the right sort of paradigm for thinking about those things so that we make a bridge between what is raw possible inside the computer and what we humans can do to kind of conceptualize what's going on. And that's a current thing of interest, which I'm hoping over the next, I don't know, maybe a year or so, we will have kind of this framework for doing multi-computation that will make that easier. Once we have that, we may be immediately saying, oh my gosh, I wish there was a form of GPU that worked in this way. And I wish one could sort of take these parallel threads and work in this particular fashion, but I don't know that yet. So I can't really say much about that yet. So I think, as I say, I think that the main issue here is has to do with this it's that you know, once you have a universal computer, you can program anything, so it sort of doesn't matter too much what that low-level structure is. All right, there are lots of other questions here that are interesting. Let me try and do maybe one or two more, and then we should wrap up for today. Zayden asks, are there laws governing the development of human history? You know, people have certainly said that from time to time. Hegel was famous for having this kind of idea of, you know, sort of this perpetual change in history. And people concluded from that diametrically opposite political kinds of conclusions of, I think it sort of broke into the left Hegelians and the right Hegelians that turned into some of the less savory stories of political organization in the 20th century and so on. But the thing that, the question is sort of, are there features of the development of society, the things that, the way that human organizations develop, are there sort of necessary features of that? And, you know, one thing that's pretty striking to see, we have in Wolfram Language, actually, we have the data on sort of all country borders known throughout history. And if you look, for example, at Europe, where there's been lots of well-defined country borders for a few thousand years, a couple of thousand years at least, you can kind of look at the time-lapse movie of, where did the country borders move in Europe? And it's really strange to see, because it looks very much like soap bubbles or something. It's just like things expand and then they pop. And, that was an empire, and then it popped eventually after it took over too much. And it looks, when you look at these things, it looks very much like a physical or perhaps biological process. It doesn't look like this was millions of people doing all these different things in all these countries and all this leadership and all these armies and so on. It just looks like something that might be a bunch of soap bubbles expanding and contracting and popping and so on. And that gives one kind of the sense that, well, there should be sort of some kind of at least statistical laws that govern how things work. I mean, it could be that there are such things. Now it has to be said that if you look at many different kinds of properties of things, what are the sizes of different countries? If you rank all the different countries in order of their population, how populous is the most populous versus the second most populous versus third, and so on. There's a tremendous tendency for the nth most popular to have a popularity of like 1 over n, or 1 over n to some power, to get some kind of power law distribution like that. And that's something you see just across all kinds of different things in kind of humanly set up systems and not so humanly set up systems, whether it's in distributions of, I don't know, city sizes, incomes, this, that, and the other. Lots of places where there are these power law distributions. Why do those come about? Well, there are a variety of mechanisms, but they tend to be things where there's some sort of hierarchical structure and things sort of build up or break down in a hierarchy. You typically get these kinds of power law types of things happening, although there are other mechanisms for doing that as well. I mean, that's a common one. So there are these statistical features where you can't necessarily say this particular city will be of this size, but you can say the distribution of sizes of all cities will look roughly like this. And maybe you can give some simple model that can explain that, and the model is robust enough that you'll finally get some result that looks like this. But if you ask the question, do empires always, I mean, in a sense, there are sort of truisms like everything eventually comes to an end. And so if you believe in that, which is really ultimately a sort of question for physics of, does the universe come to an end? And probably the answer to that is no, not really. Do things come to an end when a black hole is imploding? Eventually in a black hole, there's a point where time ends, but that's a sort of a rare case. But if you have a sort of an almost truism, everything comes to an end, you can have a law of history that every empire will eventually come to an end. But that's perhaps not a terribly useful thing to say. If you ask a question like, people have tried to come up with these kind of general laws of history, like, once you have a certain bureaucracy, the bureaucracy will get ever bigger and bigger. Or once you have a certain, once something becomes commonly done, it will end up becoming structured and institutionalized and so on. There are kind of semi-anecdotal laws that you can describe like that I think there probably is quite a bit of commonality in the way that humans operate in terms of those types of things. And it may not just be humans. I mean, just to give an example here of both an analogy and a difficulty is biological evolution. Biological evolution is also, in a sense, a historical story. There were trilobites once. There aren't trilobites anymore. There were dinosaurs. There are birds. Things evolved into things. We can even see all of that history kind of laid out in the fossil record. And the question is there a theory of that history? Is there a theory that will tell us that there should have been dinosaurs? Is there a theory that will tell us that eventually you'll get an organism that will make a theory of biology and so on? What kind of things are theoretically accessible? Or is biological evolution merely a frozen record of arbitrary history? Well, I suspect that there are general laws, and what Charles Darwin figured out in his 1859 Origin of Species book was this idea of evolution by natural selection, this idea that the species that survive, the species will be the ones that sort of, it's almost a self-fulfilling prophecy. If the species has more children, then there will be more of it, so to speak, and then that will be the surviving species, and that happens as a result of just the environment acting on the species. Now, the true story is much more complicated because the species acts back on the environment, the species acts on other species, and so on. But there is this general, there's this idea that there is this process of natural selection. And we can see why, when we look back and we look at a species that has this weird shaped beak, we can say, how did it get the weird shaped beak? Oh, it needed that in order to open the coconut or something. And it was living in a place where there were coconuts, and we can find in the fossil record that first it had this shape of beak, and then it ended up with this shape of beak that we can now understand better for opening coconuts. But the question is there a more general kind of less just explaining after the fact theory for how biological evolution works? And Charles Darwin thought back in 1859, he was pretty sure there would be. He was pretty sure, as he said, I think the last line of his book says, just as the Earth goes around the sun according to the fixed law of gravity, so ever more complex species basically are being and will be evolved. Now, nobody ever managed to figure out how to make a precise theory based on that. That's a thing we generally think to be true, but there isn't a precise kind of formal theory that can describe that. Actually, some things that are spin-offs from our physics project might give us a chance to make such a theory now. That's sort of a new thing. But even these questions about why is there so much diversity among biological species? Why isn't there just one winning species? Often in economic situations, in commercial situations, there might be one winning company, takes over everything in a particular domain. And it would be, and so why doesn't it happen with species? Well, sometimes it happens a bit more and a bit less, but in the end, there are 5 or 10 million species in the world. And why are there so many? Is it because the environment has some particular form? Is it because of some intrinsic dynamics of the process of biological evolution? Even, why do species themselves form? We kind of think that's because you get sort of the organisms are kind of moving further apart, and they can't and they get to the point where they can't mate with each other and so on. But we clearly know that isn't the full story. I mean, we all have a certain amount of Neanderthal DNA in us. I was just looking at some new report for me. What was the number? Oh gosh, I can't even remember. Was it? I think it did say you have less Neanderthal DNA than typical by a lot, actually, than typical for the population on which these tests are done, which kind of surprised me, actually, because I'm sort of a Northern European character, and I thought that was where the Neanderthals were living. I was a little disappointed to not feel more Neanderthal, so to speak. But in any case, but that's an example where clearly that subspecies, or that sort of what eventually became a separate species, there clearly was interbreeding, which we're all kind of in one way or another beneficiaries of. But in any case, is there a theory of biological evolution? Well, there isn't really. We don't have one yet. There are probably pieces to that about why there's species diversity and so on. That's sort of a separate thing. But I think that may be almost the test case for a theory of human history, is a theory of biological history, so to speak. I tend to think there's probably more that can be figured out for theories of human history. And there are more things that you can kind of, I mean, the record of people trying to figure out, oh, we have this giant model of the economy of the world, and we're going to figure out what if questions about this and that, doesn't tend to work terribly well. It hasn't traditionally worked terribly well. Now, perhaps it's not helped by the fact that there are humans in the loop. And once you predict something for humans, humans know the prediction, and then they act differently. Perhaps there's some of that dynamic. I don't know how important that is. That's certainly something people think might be important in financial markets and in understanding, some method for, I've got this amazing loop for buying this stock, selling this other thing, buying this and so on. I've got this amazing loop. I just run money through it and I'll just make money from nothing, so to speak. That loop tends to close up because kind of other people learn about that loop and the market changes so that that loop is no longer available. And that's a consequence of kind of the humans in the loop aspect of it. Loops in more sense than one. All right, last question for today, maybe. So question here from Baker asking, any tricks for reading textbooks that maximize understanding of the material? I will tell you that I'm probably a bad person to ask that question of, because I really never read textbooks sort of for the sake of reading a textbook. In fact, if I do that, I just can't remember anything. I always have to have, this is a question I'm trying to answer. Now let me go and try and answer that question by reading this book. And so in a sense, and I don't know how generalizable that idea is, but in a sense, even if you go and you look at the textbook and you look at some exercise in the textbook and you look down the exercises and you say, you find an exercise, you say, hey, that one's interesting. I'm interested in that question. Let me try and figure out, how to answer that question. Then you're sort of motivated to go and look through the book and try and fit together the things you're learning with the thing that you want to answer. I mean, for me, doing projects, answering questions, that's the way I managed to learn material, rather than sort of going through the textbook from page 1 onwards. I would say that a way that I suppose for me, okay, one of my way of learning things is to try and explain it like I do in these live streams. These live streams really help my understanding of lots of kinds of material, because I'm realizing I'm trying to explain it, and in explaining it, I'm understanding it better myself. And I would say that as you explain it, if you explain it, and particularly if you imagine explaining it to perhaps somebody who knows significantly less about the material than you do, if you're explaining it to the teacher who knows more, you're going to say, well, of course you know this, blah, 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 blah. And you never really have to engage on the question of what's the fundamental issue that you're trying to think about here. So I think, one of the things is, can you break it down to the point where you could explain the material to somebody who knows a lot less about it than you do? Can you sort of simplify the material in your own mind and in your exposition so that you can explain it to somebody else? I think those would be methods for getting to the point of understanding things. Now, I've been myself recently, I mean, the topics I've been trying to learn, I was trying to learn a bunch about economics. Last year, that's been put on hold for a little while now, and it probably will come back in a few months. I've been learning about philosophy and the history of philosophy, and that's one where, honestly, I would never be able to learn that if I didn't have specific questions and sort of attachment points of what I'm trying to know about. Now, a little bit, I'm also, in that particular case, it's like, well, I've heard of this person or this person or this person. What on earth did, let's say, Hegel, for example, I've heard of him, and I've heard of sort of the meta things people say about him. And then it's kind of like, well, what did he actually say? Let me try to understand that. And I'm then motivated to understand that just as a matter of filling in my general knowledge, because it's something I vaguely heard about. But if you say, here's this philosopher whose name I've never heard, let me tell you about that person, it's going to be really hard for me to remember that unless it somehow connects to some particular issue in philosophy that I've been really interested in. So I would say that in that case, for me, learning, and I don't think I've adequately learnt the history of philosophy. I'm in a couple of months, I'll probably write something on the relationship between the history of philosophy and theology to the things we've done in our physics project. And then I will understand it much better. Because once I understand, what did Heraclitus really say that we can now have that I now have an intrinsic understanding of from other things I've done, I have a much better chance. Well, in this case, very little of that. That's a bad example, but let's take somebody where the works survive, like Immanuel Kant, for example. What did Kant really say about the nature of space and time? well, now that I think I have a good understanding of the nature of space and time, I can now go back and say, did what Kant said plug in? How does it plug into my understanding? And then I have a chance to really remember it and understand it myself. Another area I've been learning is immunology. That's an area where, well, just reading the books is like, I did try that. It's pretty, I drown trying to do that, because it's an area where there's a huge amount of detail that's known about, oh, the CD8 positive T cell that is, is signaled by interleukin 2 and IL-2, and there's this pathway and that thing and that thing. It's like, I don't know what's going on. I could probably memorize this if I were, going to medical school or something, and, I had to memorize it. I probably, I have a decent memory, so I probably could outright memorize it, but I don't think I would really, I wouldn't be able, that would be a very bad way to learn that stuff. And how will I learn that stuff? Well, I've been learning it, but partly that's because I sort of have these little theories for pieces of how the immune system works. I wonder if this works this way. And then I can, in other words, part of what I'm doing is getting to the point where I could explain how this works. How does the the light chain of an immunoglobulin, how does it recognize molecules? Well, then I have questions. Given the particular sort of sequence of transposable elements in the genetics that makes that, how exactly is that protein loop produced? Well, not produced, I know how it's produced, but what is the diversity of shapes in that protein loop? And that's something which, with modern protein folding technology that's existed for the last year or so, it should be possible to actually enumerate what those possible structures are like. And then for me, okay, oh yeah, I forgot another critical part of my way of understanding things is try and actually write a program that relates to what I'm trying to understand. So actually writing computational language, some case of this. So for example, in the case of immunology, I absolutely will try and take these things and represent them and try and see, well, what actually do these loops of protein look like? And let me generate 100 of them. Let's see what they look like. Let's see how they would fit around an antigen, how a piece of antigen, let me try to understand how that works. There's some pathway here. Let me actually get a graph that represents that pathway and see what consequences it has and so on. And that's at least for my way of understanding things. If I can turn it into a piece of, I should have said this, I mean, if I can turn it into a piece of computational language, then I really understand it. If I can turn it into a piece of natural language and explain it, that's also a good path to understanding. But the computational language part is a really wonderful way to understand things. And by the way, if you do that, you probably will understand it better than almost anybody else understands it. And the thing that's really neat is once you've understood it at a computational language level, it's not just you on your own being able to make use of that knowledge. Your computer is at your side, so to speak, being able to make use of it with you. And that's a really powerful thing. And lots of things I've discovered, for example, are a consequence of that kind of methodology. And it's really remarkable. I mean, I would say that, well, I'm take the example of particularly one of my kids, who is a very sophisticated computational language user and so on. When he was kind of studying things in high school and college and so on, did all kinds of random courses, and each one, it seemed like he would sort of take random things that were coming up and sort of turn them into computational language. And then it's like, show them to the professor, and it's like, oh my gosh, I've never seen something like that before. But it was trivial. It was, once you've been able to translate it into this sort of powerful medium that is a very new medium, you're able to jump further than people have ever seen before. And that's a really neat thing to be able to do. And it's also a really, really good way to truly understand the material. So that's a few comments on that. I think, as I say, I've got this case right now because I'm kind of about to start talking to immunologists about trying to understand things about modeling the immune system using methods that come from our physics project. And I'm a little bit shy to start talking to immunologists until I know the kind of basic lingo of how the immune system works, because otherwise it's like somebody tells me it's a helper T cell, and it's like, I don't know what that is. I do know what that is now. I haven't known actually that one for a while, but you know, or getting confused about sort of basic aspects of it. I've got to get to the threshold place where I can actually have a reasonable conversation, even if I'm not going to know or not even going to care what all of the, you know, what all of the particular surface proteins on cells are, and what all their particular names are, and what particular tricks the innate immune system has learned in rebuffing different kinds of things that can attack it. That doesn't really matter for the kinds of things I'm trying to think about. So I need to know a little bit of that as sort of general background knowledge, because one thing when you study one of the things that happens when you study things, and actually there's another point to make, is that every field has a way of thinking about things, and it's different from field to field. So for example, I was just doing actually a thing that probably will get posted, a interview discussion with a chap called Judea Pearl, who's worked on probabilistic reasoning and probabilistic modeling and causal models and things like this. I was just doing a discussion with him, and one of the things that's interesting is that somebody who's worked on sort of probabilistic and statistical things and about the way that sort of cause and effect works in those domains, there's a certain way of thinking about things that one develops from that. And it's not one that I have. So it's one that I kind of have to try and absorb, but it's a different way of thinking. So for example, a typical case is in economics, let's say, or in evolutionary biology, both things. If somebody says, I see a bird and it's got a red beak. Okay, to an evolutionary biologist, or I see a bird, it's got a red beak, it eats birds with, or it has, I don't know, it has a parasitic worm, no, a symbiotic, you know, insect that has green wings and does this or that. To an evolutionary biologist, there'll be a way of thinking about that says, well, if it's got a red beak and it does this, then there'll be more of that species than this species, because that's just the way evolution works, because they've got a way of thinking about things like that. In economics, it's like, why did somebody do this? Well, in economics, it's often, well, because there's this sort of rational thing that you're doing that's maximizing this utility of this, and there's a way of thinking about it. Same thing in lots of other fields. There's sort of ways of thinking about things, and sort of penetrating into the way of thinking about things in a given field is one of the big challenges. And I think in my experience, the best way to do that is just doing examples, so to speak, learning about things, and often thinking about them the way you would thinking about them, and then seeing how they get thought about in that field, and seeing sort of the tweak to the way that you were thinking about them. That's the way of thinking about them within that field and within the particular sort of methodology and cognitive framework that exists in that field. I mean, in mathematics, for example, people, you know, just sort of an almost a joke type thing is people say, oh, I'm trying to prove this thing. I've got this mathematical thing. And the mathematician will say, well, what about the case of zero? What about the very trivial case? That's a sort of a thing in that way of thinking about things. Well, start with the trivial case. Let's look at it for that case. That's sort of a thing you might do. Whereas in another field, it's like, you know, in biology, for example, it's you're thinking about this, you know, let's think about the case where the woodpecker lived at the top of a skyscraper. You know, that's a corner case, but that's not the case you'd think about. You'd instead be thinking about something that will be very different from the kind of mathematical way of thinking. Anyway, all right, well, I think that's probably it for today, but thanks very much for lots of interesting questions. We have more saved up for next time, and I look forward to getting more questions and seeing what I can do to answer them, and exercising my method for learning things, which is in this case trying to explain them. So thanks very much.